Hey there, future scientists. So, here's a fun question to start with. Why does it take forever to boil a pot of water compared to heating up a metal spoon? Ever wondered why some things heat up faster than others? Well, it's all about something called specific heat capacity. Specific heat capacity tells us how much energy is needed to change the temperature of a substance. In simple terms, it's the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. Sounds complicated? Don't worry, we'll break it down. The equation that represents this is Q equals m into C into delta T, where Q is the heat added, m is the mass, C is the specific heat capacity, and delta T is the change in temperature. So, water needs more energy to heat up than metal does, and that's because water has a high specific heat capacity. It takes longer to change its temperature, which is why it's used for things like heating pads and coolants. Now, let's see how heat and temperature change work together. When heat is added to a substance, the temperature goes up, but not all substances react the same way. Take water, for example. Water has a high specific heat capacity, meaning it takes a lot of heat to raise its temperature by just 1 degree. But metals? Not so much. Metals like copper or iron heat up quickly because they have a low specific heat capacity. Here's the equation again, Q equals m into C into delta T. The amount of heat added depends on the mass of the substance and its specific heat capacity. For example, when you add the same amount of heat to a metal spoon and a cup of water, the spoon gets hotter faster because it has a much lower specific heat capacity. Let's go a little deeper and figure out how we calculate specific heat capacity. Here's how we can rearrange the formula to solve for C, the specific heat capacity. From the equation Q equals m into C into delta T, we can isolate C equals Q by m times delta T. This equation tells us how much heat we need to change the temperature of a substance, and by measuring how much heat is added and how much the temperature increases, we can calculate the specific heat capacity of any material. So, if we have a material with a known mass and we heat it by a certain amount, we can figure out its specific heat capacity by tracking the temperature change. Alright, now let's talk about the units. The specific heat capacity is measured in joules per kilogram per degree Celsius or joules per kilogram per Kelvin. So, let's say you're heating 1 kilogram of water by 1 degree Celsius and it requires about 4,184 joules of energy. That's the specific heat capacity of water. To measure specific heat capacity, we can use an experiment like the calorimeter method, where we carefully measure the heat energy added to a substance and track the temperature change. It's a fun way to get your hands dirty and see how heat really works. Time to solve a real-world example. Let's say you have 200 grams of water and you add 1000 joules of heat to it. The temperature increases by 5 degrees Celsius. Now, let's find the specific heat capacity of the water. We'll use the formula Q equals m times C times delta T. Now, rearrange it to find C. C equals Q divided by the product of m and delta T. Now, plug in the values. C equals 1000 joules divided by the product of 0.2 kilograms and 5 degrees Celsius. C equals 1000 divided by 1. C equals 5000 joules per kilogram per degree Celsius. That's the specific heat capacity of the water. It's 5000 joules per kilogram per degree Celsius, which matches the known value for water. This tells us how much energy is required to raise the temperature of 1 kilogram of water by 1 degree Celsius. So, to wrap it all up, thermal equilibrium isn't just some boring term, it's how everything around us balances out. When two objects are in contact, They'll exchange heat until they reach the same temperature. Thanks to the zeroth law, we can even measure temperature using thermometers, knowing that if two things are in equilibrium with each other, they're the same temperature. From your morning coffee to the way your car manages heat, thermal equilibrium is always at work, making sure everything's in balance. Keep this in mind next time you find yourself touching a cup of coffee. It's all about finding equilibrium.